In this lesson, we discuss how to build a ring of fractions from a given commutative ring. So the goal of this lesson is to show that every commutative ring R is always a subring of a larger ring Q which we're going to call the ring of fractions, in which every non-zero element of R that is not a zero divisor is a unit in Q. The main application of this will be to integral domains, in which case the ring of fractions Q will be a field called the field of fractions. And so this whole process mimics the construction of the rational numbers from the integers. So we proceed by mimicking the construction of the rationals from the ring of integers. So first, we will review some basic properties of fractions in Q. In the rationals. So we know that every element of the rationals can be represented in an infinite number of ways. So each element of the rationals can be represented in an infinite number of ways as a fraction of integers. So for example, 1/2 is the same as 2/4, which is the same as 3/6, and so on. So we can continue this indefinitely. But these representations are related by the following equation. So the fraction AB equals CD if and only if, so by cross multiplication, we have AD equals BC. So it's this equation, AD equals BC, that we can use instead of using the fraction form when dealing with arbitrary rings. So we can actually define an equivalence relation on the integers by saying that the ordered pair AB is related to the ordered pair CD if and only if AD equals BC. So then we look at the fraction A over B, and we look at this as an equivalence class. So this is the equivalence class of ordered pairs AB of integers with B not equal to 0. So we can define operations on these equivalence classes of fractions by A over B plus C over D will equal AD plus BC all over BD, and the multiplication of two fractions, we know that A over B times C over D will equal AC over BD. So we're going to use these same ideas to construct a ring of fractions from any given commutative ring R. So let's state our main result here, this theorem. We're going to let R be a commutative ring and we're going to let capital D be any non-empty subset of R that does not contain 0 does not contain any 0 divisors and is closed under multiplication. So if we multiply any two elements of D, we obtain an element of D. Then there's a commutative ring Q with identity such that Q contains R as a subring more precisely, it will contain an isomorphic copy of R as a subring, and further, every element of D is a unit in Q. Further, every element of Q is of the form RD inverse for some element R in the ring R and D in the set D. So in particular, if D equals everything in R except for 0, then Q will be a field. And note, so once we finish proving this, we can see that the construction of the rationals from the ring of integers is a special case. And indeed, the construction of the rationals from the integers is the motivating example for this theorem. Let's begin a proof. Let capital F be the set of ordered pairs RD, where R is in the ring R and D is in the subset D, and we're going to define a relation tilde on F by AB is related to CD if and only if AD equals BC, which again, remember, this was similar to the idea of two fractions being equal in the rationals. Now we're dealing with an arbitrary ring, so we have the product AD equals BC if and only if two ordered pairs are related. Then this relation is an equivalence relation. So let's show this reflexive. So for any R in R and little d in set D, we have that RD equals DR, because we're in a commutative ring after all. And this equation shows that RD is related to RD. So this relation is reflexive. To show that it's symmetric, let's assume that AB is related to CD. So we need to show that CD is related to AB. Well, then AD equals BC. But again, since this is commutative, this is the same as saying that CB is equal to DA, which shows that CD is related to AB. Now for transitive, let's suppose AB is related to CD and CD is related to EF. And we need to show that AB is related to EF. Then we know that AD equals BC, and hence AD minus BC equals 0. And we know that CF equals DE, so we have CF minus DE equals 0. Then if I multiply the first equation by F and the second equation by B, we have f times AD minus BC equals 0, and b times CF minus DE equals 0. Then using the distributive property, we have ADF minus BCF equals 0, and BCF minus DEB equals 0. But if we add these two equations together, we obtain the equation ADF minus DEB equals 0. And if we factor out a D, this implies that D times AF minus BE equals 0. But recall that little d is an element of the subset D, so therefore little d is not 0, and it's not a 0 divisor. Since D is in capital D, D is not 0, and D is not a 0 divisor, so from this last equation, we must conclude that AF minus BE equals 0, since D times this equation was equal to 0. But this is the same as saying that AF equals BE, and therefore AB is related to EF. So we see that this relation is an equivalence relation. So now I want to denote the equivalence class of RD by the fraction R over D. So this will be the set of all ordered pairs AB, where A is in R and B is in D, and AB is related to RD. That means that RB equals AD. And we're going to let capital Q be the set of all equivalence classes under the operation tilde. Now, we're going to point out a fact that the equivalence class R over D equals the equivalence class RE over DE in Q for all elements in E in the set D, since we assume that D is closed under multiplication. So now we're going to show that Q is a commutative ring with the following operations. So I'll show that Q is a commutative ring with identity. Under the operations A over B plus C over D equals AD plus BC over BD, and A over B times C over D equals AC over BD. So again, these operations mimic the operations of the fractions in the rational numbers. Now these operations are defined on the set Q of equivalence classes. So first we want to show that these operations are well defined. That is, the sums and the products don't depend on the particular representatives of the equivalence classes. So first, let's show that these operations are well defined. So let's suppose that A over B is equal to A prime over B prime, and C over D is equal to C prime over D prime. Then we know that A B prime equals A prime B, and C D prime equals C prime D. So we must show that the sum AD plus BC over BD is equal to A prime D prime plus B prime C prime all over B prime D prime. And that's the same as showing that B prime D prime times the product times the sum AD plus BC equals A prime D prime plus B prime C prime all times BD. So let's look at this last equation. The left-hand side equals A B prime D prime D plus C D prime B prime B. We have some substitutions we can use. So this equals A prime B D prime D plus C prime D B prime B. And then this quantity equals the right-hand side. When we just distribute the BD in the right-hand side of this previous equation. So we see that addition is well defined. Now for multiplication. So we must also show that AC over BD equals A prime C prime over B prime D prime, which again is equivalent to AC B prime D prime equals A prime C prime BD. But this equation follows from multiplying AB prime equals A prime B together with CD prime equals C prime D. So thus multiplication is well defined as well. So the operations we've defined on Q are well defined. Now second, the addition that we just defined makes Q into an abelian group where the additive identity is 0 over little d for any little d in the set capital D, and given any element of Q, the additive inverse of A over D is negative A over D. Third, one could check that this multiplication is associative, distributive, and commutative. Again, this follows from the structure of R as a ring. And fourth, the multiplicative identity of Q is D over D for any little d in set D. And we see this because A over B times D over D is defined as AD over BD, which we pointed out is equal to A over B. So thus, we conclude that Q is a commutative ring with identity. So now we'll show that Q contains R as a subring. So now we embed R into Q by defining the following map. Let's call it phi from R to Q by phi of R equals RD over D for some D and D. Now the value of phi of R is independent of the choice of little d, since RD over D equals RE over E for all D and E in the set D. So we see that phi of R does not depend on the choice of little d. Now this map is a ring homomorphism. So let's look at that. So since phi of R plus S equals R plus S times D over D, but this also equals R plus S times D squared over D squared, because D is in capital D. And then I can distribute the D squared, so this is R D squared plus S D squared over D squared. This is the definition of RD over D plus SD over D, which equals phi of R plus phi of S. And similarly, phi of RS equals RS D times D, which again it can be written as RS D squared over D squared, and this is RD over D times SD over D, which equals phi of R times phi of S. So we see that phi is a ring homomorphism. But further, phi is actually 1-to-1. Because if phi of R equals phi of S, and that implies that RD over D equals SD over D, which implies that RD squared equals SD squared. And if I move everything to the left and factor out the D squared, this tells me that R minus S D squared equals 0. But recall that D is an element of the set D, and therefore D squared is also in D. And so D squared cannot be a 0 divisor, and D squared cannot be 0. So therefore, R minus S equals 0. So again, this follows from the fact that D is in capital D. And so therefore, we see that R equals S, and phi is 1-to-1. So therefore, the image of R is a subring of Q, and this image of R is actually isomorphic to R. So therefore, the subring phi of R of Q is isomorphic to R. So we can identify every element of R with phi of R, and so therefore we can consider R as a subring of Q, although technically it's actually an isomorphic copy of R. So we now identify each element, little r and r, with phi of r. And so we can consider R as a subring of Q. So the last claim that we have to show is that every element of the set capital D is a unit in Q. So finally, we show that every element D in the set D is a unit in Q. So let little d be represented by dE over E in Q, again for some element in E in the set capital D. Then dE over E times E over dE equals dE squared over dE squared, but this is the identity in Q. Since dE squared is an element of capital D because capital D was closed under multiplication. So thus the inverse of D is the element E over dE. And we see that D is a unit in Q. So if the element R over D is in Q, then R over D equals RE over dE for any element E in capital D, but this is the same as R times D inverse so in particular, if D is equal to all of R except for 0, then every non-zero element of Q is a unit, and hence Q is a field. So this finishes all of the claims of our theorem. Now for some quick definitions. 1, the ring Q is called the ring of fractions of D with respect to R. And is denoted by D inverse R. Secondly, in a special case where R is an integral domain, and D equals R minus 0, and we saw that Q is actually a field, and Q is called the field of fractions. of R. So again, the motivating example is the fact that the ring of rational numbers is the field of fractions of the integers.